All right, we are going to look at the Milestones Unit 1 review, and I am going to work through with you on the things that you need to know about Unit 1. All right, so first up, the big topic in Unit 1 was transformations, and basically that's going to be talking about a translation, a reflection, a rotation, and then we also discussed dilations in Unit 1. So only translating, reflecting, and rotating are going to keep the figure the same size. If you dilate, that's when you change the size of the shape. All right, so let's focus first on translations. So translation is a slide on the graph. I kind of highlighted SL right there, if that helps you remember that it's a slide. The slide can go straight up and down, it can go right to left, or it can go diagonal. So it just depends. The way we know that it's a translation is because there is something added to the X and the Y. And that's why the shape is moving. Because if we add something to the X, it's going to cause the X to move to the right because the X value is going to get bigger. Or if we subtract, that's going to cause the X to go left because when we subtract, the X value is getting smaller. So there's a few ways that translations can be written. This is the one that is used in Algebra 1. You could also write it in words. So how about we translate right 5 and down 6. Okay. Another way we could write that is if we said that we were going to translate by that amount, or like we said, we could say that we're going to do x plus 5 and y minus 6. So what's going to happen is if we look at this shape, I'm just going to take some important points here to get me started. So if I take this point right here, I need to move it 1, 2, 3, 4, 5, and then down 1, 2, 3, 4, 5, 6. So the point of my arrow is moving from there to there. So what that means is that all of the rest of the points are going to do the same thing. So let's do this one next. So we need to go right 5 and down 6. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, which brings, whoops, that one right there. All right, let's try this one. Right 5, down 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. All right, now I'm going to pause because even though a translation means that every single point is moved by that amount, at this point, I'm just going to run a quick check. And I can see that from here to here, I go up 2 and left 2, which is the same thing that happened right there. And then I can tell that to get from this point to this point, I'm going down to left 2, which is what happened right there. And really, from here, I can probably just sketch the rest of my shape. And I need to go 3 spaces out, and then down, and then back. So that's a translation of 5, negative 6. All right, next up is reflection. So reflection is when we flip the shape on the graph, and we can do this over any line on the graph. So we can reflect over the x-axis, we can reflect over the y-axis, we can reflect over any horizontal or vertical line. We can even reflect over diagonal lines. All right, so how about on this one, let's reflect over the y-axis on this one. So this right here is the y-axis. So what I want to do is I want to take this arrow from here and I want to flip it over here. So basically this point is going to stay where it is. This one is 2 spaces to the left of the y-axis, so when I'm done, it should be 2 spaces to the right. And then this right here is 2 spaces to the left of my reflection line. So when I'm done, it should be 2 spaces to the right. And then again, we can probably at this point just finish the rest of our shape. So that's a reflection over the y-axis. All right, for this one, let's reflect over the x-axis. All right, so here's the x-axis right here. So what I know about this point is that it's 3 spaces above the x-axis. So when I reflect it, it needs to be 3 spaces below. This one right here is 1 space above, so its reflection is going to be 1 space below. This one right here is 1, 2, 3, 4, 5 above, so 1, 2, 3, 4, 5 below is its reflection. And then again, I can probably just sketch the rest of my shape from there. So what happens when we reflect over the y-axis, the sign of the x changes, because instead of going left, we go right. And then when we reflect over the x-axis, the sign of the y value changes because, whoops, instead of going up, we're going to go down. All right, next up is rotation. And a rotation is a spin or a turn on the graph, if you want to think of it that way. We can do rotations of any kind, but in Math 8, we concentrate on 90 degrees clockwise, 90 degrees counterclockwise, or 180 degree rotation, and that one doesn't matter whether you go right or left. Now, whenever we rotate 90 degrees, basically what we're doing is we're rotating our quadrants. So this quadrant is going to move there, that one's going to move there, that one's going to move there, and that one's going to move there. That's if we do a 90 degree clockwise. So what this means is that if we take this shape, and I'm going to show you on the patty paper, and you could easily do this with your paper during even an online test. You can just hold it up to the screen on the computer. But I just traced over my shape. I'm going to hold this right here, and I'm going to turn 90 degrees clockwise, which means I'm going to turn like that. And so I'm going to end up with an arrow that's going down instead of the arrow that's pointing to the right. And what I know about this arrow is since it was 3 spaces up when it was here, its point is going to be 3 spaces right over here. So I know that's the point of my arrow right there. And then this one, if we look, again, I'm just setting it on top, rotating 90 degrees, and my left point right here, which was 1 space away, is still 1 space away, which means it's right there. And then again, once you get the gist of it, you can probably just go ahead and sketch the rest of, whoa, yikes, that wasn't that great, the rest of your shape. All right, so on this one, let's try 90 degrees counterclockwise. So this is going to move here, this one's going to move here, that one's going to rotate there, and that one's going to rotate here. So what I know is that this arrow should end up in this quadrant down here. All right, now I have the same picture, so I'm going to use this again. And this time, I'm rotating 90 degrees counterclockwise, which is the opposite way that a clock goes. So it's going to go down like this. So same thing as before, instead of being 3 spaces up, now I'm 3 spaces left. So I know that the point of my arrow is right there. And this one was 1 space away from the x-axis, which means it's going to be 1 space away from the y-axis once I rotate it. And then again, we can pretty much just draw our shape. All right, last one, let's do 180 degrees. Oh, I forgot to label this. This is 90 degrees counterclockwise on that one. All right, so let's do a 180 degree rotation. So what's going to happen is we're going to skip over, and well, we're moving 2 quadrants, so we're going to skip the one and go to the next one. So what happens is basically that one's going to go to there, and this one would come up here, and then whatever was in here would move there, and whatever's there would move there. So it's basically a movement across the, like diagonally to the next quadrant. So let's start with this one. Now, it should make sense that 180-degree rotation doesn't matter because we could go, there's one quadrant, there's the second one, or we would end up with the same thing if we went 1 and 1 on that one. So basically what's going to happen is we're going to end up with the same arrow, but instead of pointing to the right, it's going to be pointing to the left. So this one is 3 spaces up, so that points 3 spaces down. I know this one is 1 away from the X, so this one's going to be 1 away from the X. And then once we get that, we can probably go ahead and draw the rest of our shape in. All right, now I should make a quick mention that 90 degrees clockwise is the same thing. So let's say that is the same thing as 270 degrees counterclockwise. And 90 degrees counterclockwise is the same thing. Oh, I didn't write 270. I wrote 27. Well, good thing I'm using my erasable pen here. So 270 degrees counterclockwise. So, and basically, I think this should make sense, is since each quadrant is 90 degrees, if I go 1 turn to the right, that would be the same thing as making 3 turns to the left. All right, done with page 1. Okay, next up, talking about dilating. So when we dilate a figure, we change the size. So we're still going to have an arrow, we're just not going to have an arrow that's the same size. It's going to be either bigger or smaller depending on what we multiply by. And I think it makes sense. If we multiply by 1, our figure doesn't change. Our numbers don't change when we multiply by 1. If I multiply by something bigger than 1, I should get a bigger answer. And if I multiply by something smaller than 1, I should get a smaller answer. So for this one, let's dilate with a scale factor of 2. Well, what that means is that my shape is going to end up being 2 times bigger. All right, all we have to do is multiply our number, which is 2, to each point. So I'm going to start with this point right here. This is the point 2, 1. If I make the point 2, 1 2 times bigger, it's going to become 4, 2. So that is my new arrow point. All right, let's take this one right here. This point is 0, 3. Did I count that right? 1, 2, 3. So this point is the point 0, 3. And if I make that point 2 times bigger, it's going to be 0, 6, which we'll just pretend, but it is right there at the end. So this piece right here is twice as long as that piece right there. All right, this one right here is 0, negative 1. So 0, negative 1, if I make that point 2 times bigger, it's going to be 0, negative 2. So now I have this side right there, and that piece is twice as big as that piece. All right, let's take this point out here. 1, 2, 3, 1, 2. So this point right here is the point negative 3, 2. Negative 3, 2. And if I make that point 2 times bigger, it's going to be negative 6, 4. So negative 6, 4, I'm going to say it's right up there. So now you can see that our shape is starting to come alive here on our graph. So at that point, I think I am okay with drawing it the rest of the way. So the arrow that I ended up with is twice the size of the original one. All right, so for this one, let's try a scale factor of 1/2. So this one should get smaller because I'm multiplying everything by something smaller than 1. All right, so here we go. This one right here is the point 2, 1. Well, if I make that point half of the size, it's going to be the point 1, 1/2, which is kind of weird. There it is right there. All right, let's go with this one right here, which was the point -3, 2. So if I make -3, 2 half of its size, that would be -1.5 and 1. So I'm going to go right there. So these things end up getting a little bit tight in here. This one is like really, really tight. But so if you just continue on, you're going to end up with an arrow that's half the size of the original one. That's crazy small. All right, so now we're going to talk about similar figures. Okay, so similar figures are when you have two shapes that have the same basic shape, but they've been dilated. So one of them is bigger than the other. And what we're going to do is make a fraction to figure out what the scale factor is, which is basically what happened up here. The easiest way to do that is to do new over original. So let's say this is our original shape, and this one over here is our new shape. I'm going to give you some measurements. So let's say this one is 15 and this one is 10. All right, to figure out what the scale factor is, I'm going to do new over original. So the scale factor is always going to be the new shape, which is 15, over the original shape, which is 10, and I can reduce both of those by 5. So that tells me that the scale factor is 3/2. All right. So let's say, just for another example, so let me change colors just so you can see another problem. Let's say this one is 20 and this one is 16. All right, so new over original. So the scale factor is going to be the new shape over the original shape. And I can reduce both of those by 4. So that tells me that the scale factor would be 5/4. All right. Okay, next up we're going to look at some triangles and some special situations that happen when we have different types of triangles. So first up is the sum of interior angles of a triangle. I think you probably have learned this before. I don't think this is new material, but the sum, which means if we add the 3 angles inside of a triangle, it's always going to be equal to 180 degrees. So let's say this one down here is 80 degrees. And let's say this one down here is 70 degrees. Could you figure out what that angle is? And hopefully your answer is yes. Because what I know is that this angle plus this angle plus that angle have to add up to 180. So, however you want to think about it, but we can see right here that we already have 150 degrees. So if we already have 150 degrees, how many degrees is the x worth if the total triangle is going to be 180? So lots of ways, just simple thinking about it, this angle up here would have to be 30 degrees. All right, taking a look at this one, I'm going to do this, and then I'm going to say that. All right, so you might say, wait, I only gave you one measurement. Hopefully you know that this, when we make a box in the corner, that tells us that's a right angle, which means it's worth 90 degrees. So I know this angle is 90 degrees. So again, if I'm trying to figure out the missing angle up here, if I add together what I already know, I get 108 degrees. So what measurement does this angle have to be in order for all three of them to add up to 180 degrees? And if you do a little bit of subtracting over here, you can figure out that this angle has to be 72 degrees. All right. Next up, the sum of the exterior angles of a triangle. So this one is kind of crazy. It's very cool. But what happens here is that if we know the angles inside of the triangle, we can figure out what would happen outside of the triangle. But in the end, if we were to move around this triangle in a circle, it would be 360 degrees. So what that tells me is that if I told you that, let's say this one is 100 degrees, can you figure out what this angle is? Hopefully you know that when we have an angle, a line that's split, that has to add up to 180. So that tells me that one right there would have to, oh my gosh, I did it again. I think my degree is throwing me off. So that has to be 80 degrees. All right, so if this one is 100, let's just say that this one right here is, let's say this one's 150 degrees. So if this angle right here is 150 degrees, do you know what this one in here would be? Well, hopefully you're thinking 30 degrees because those two have to be 180. All right, so now let's look at what we have. We know this one is 80 and this one is 30. Let's figure out what this angle is right here. Well, from what we learned just above, I know that 80 degrees plus 30 degrees plus the missing one has to add up to 180 degrees. Well, these two add up to 110 degrees. So that tells me, doing some simple subtraction here, that this one down here must be 70 degrees. All right, well, let's turn it this way, even though I wrote 70 over there. If this is 70 degrees, then what does this one need to be? Well, in order to make that 180, that has to be 110 degrees. So now, look at what we have. We have 150, 100, and 110. And if we added those three angles together, that gives us 360 total degrees. So that's just a neat thing that happens with a triangle. All right, last thing is the exterior angle theorem, And this one is pretty nifty. It goes along with what we were just doing. But if you notice back here, and maybe you noticed while I was doing this one, this angle right here is 100 degrees. And look at what the sum of those two. That's 100 degrees. So this really cool situation happens that if I know this angle out here, so let's say this one is 140 degrees, okay? And I know that this one is, oh, I don't know, let's say this one is 50 degrees. If this one is 140 and that one's 50, I can figure out these two missing angles, and I can do it a few ways. But if I wanted to know what that angle was right there, the angle that's outside of this angle, so this 140 degrees, is going to be the same as the two other angles added together. So I know that if I take 50 degrees plus whatever that is, I need to get 140 degrees. So if we do some subtraction here, I can figure out that this angle up here is 90 degrees. But it's just a neat thing that happens. And if you look at the other angles, it happens all three directions. So if we look at this one out here is 150 degrees, and those two added together are 150 degrees also. And then let me get one more color. And then if we look at this one out here was 110. These two added together equal 110. So that one is the same thing. All right, good work. Okay, last thing, this last page has to do with parallel lines and a transversal. And what happens here is that we have two lines that are parallel, and the symbol for parallel is when we do a little arrowhead like that. So these two lines are parallel, and a third line comes by and crosses them. What happens is it creates 8 angles. So I'm going to number them so you can see there are 8 different angles that are created when two lines are intersected by a third line. And if those two lines are parallel, these types of angles down here are created. All right, first up, vertical angles. So vertical angles, we're just looking at one intersection. We're not really using both of the parallel lines, but if we just look at one set of the parallel lines, we'll get vertical angles. I like to call these bow tie angles. I just think of them if you had like a little bow tie, or whatever. It's kind of what it makes me think of. But what happens, the angle on this side is going to be equal to the angle on that side. So if I know that this angle over here is 36 degrees, I know that this one across from it is also 36 degrees. So they have the same vertex, they meet in the middle, but they're going in completely opposite directions using the same two lines. So those are congruent angles. And just to make sure you know, the symbol for congruent is an equal sign with a little wave over it. All right, corresponding angles. Corresponding angles are angles that are in the same position but on a different intersection. So I basically say they're on a different corner. So that helps if you need help remembering corresponding. They're on the same corner. So this one right here, if I color that one in, is going to match up with that one right there. All right, I'm going to do some color coding here. This angle out here is on the same corner as that angle right there. And then we have two more sets. So this one down here would match up with this one down there. And then the last one, this one right here, matches up with that one right there. And again, those are congruent measurements. So let's say that I told you, that this one was 95 degrees. I know that this one down here is also 95 degrees. So corresponding or on a different corner, or same corner, different intersection. All right, next up, alternate interior angles. They're alternate because they're opposite, interior because they're inside. So what that means is that we're talking about angles that are on opposite sides of our transversal line, but they're inside of the parallel line. So alternate because they're on opposite sides. So one is on this side, one is on that side, but they're both inside of the parallel lines. And then here's another set right there. And again, those are congruent. So if I told you that this was 123 degrees, I know that this one is also 123 degrees. All right, alternate exterior angles are almost exactly the same thing, except they're exterior, which hopefully you're thinking, oh, that means they must be outside of the parallel lines, and you're correct. So this one up here is outside of the parallel lines and above. This one down here is outside of the parallel lines and below. And then we have the same thing on this side. So this angle is above the line, outside of the parallel ones. This one is below the line, outside of the parallel ones. And again, if you knew this was 61 degrees, then you know this one is 61 degrees, and that's alternate exterior angles. All right, consecutive interior angles. So what's happening here is they're interior, just like these were interior, but they're consecutive, not alternate. So what that means is they're on the same side. So this angle right here, this angle right here is inside of the parallel lines, and so is this one. Inside the parallel lines, but they're not on opposite sides, they're on the same side. So those are called consecutive. Well, these are the only ones that are not congruent, but they are supplementary, which means that they add up to 180 degrees. So let's say that I told you this one right here was 70 degrees. Then you could figure out that this one down here would have to be 110 degrees. All right, that covers Unit 1. If you need to back it up and review anything, it is a video, so you have that option, and we'll move on to the next unit.